induced by Vz because our shear Yz due to Vz is equal to 0. Okay, so it requires less work on this one, but you have to be careful with the first moment of area over here. Okay, so over here, you have to be really careful, okay, when you calculate the first moment. Okay, down here you have to be very cautious. Okay, so if you were to ask me, what do I think about this problem? This is one of the, if you look at this question, okay, this is one of the worst. Okay, if you can solve questions like this, when I say this is one of the worst, why I made that statement is because it has a lot of load components, right? It has a 25 kilonewton, right? It has the 2 8s, and it has 100 kilonewton from the top. One of the worst you have seen. Okay, I'm going to do another example. Before I go on, anyone, any questions, please?
Can you re-explain the direction of shear stress for element A?
Okay. So for element A, right, you look at the shear flow of element A due to Vx is going from right to left, right? You can see the design over here. Yes.
Yeah.
Then on the shear flow due to Vy, the direction flip. It gone opposite. Yes.
Yes.
Okay. So when you do the summation, so that's why I draw the direction down here. Okay. So you have one direction going one way, the other one going the opposite way. So the higher shear will like you just minus off, and you know that this direction will be dominant, right? So that's why you move it in this direction over here. Okay. Because they're opposite in direction. That's all.
Okay. Yeah.
Okay. As I say, this is the first time you're saying it. I think when you do the homework, then you get more used to it, then you got more confident. Okay.
Yeah.
Right.
I
So
thought so on VZ, if you know, I mean VX,
mm,
if you go up a bit.
mm.
Did we not say, was it this one? Yeah, here, no, maybe the one before. Up more. It's where we calculated it was 0. The shear is 0 because, like you said, it was because there's a terminal.
Yep, this one.
Yeah, this one, yeah. I thought if they come together, there's no terminal.
No, they come
Is
together, it's a terminal.
it's a terminal?
Yeah.
So
Okay,
is it
wait. When they meet and got nowhere to go, or it leaves, then we call it a terminal. Right? This is called a terminal. Yes or no?
yeah,
Right.
yeah.
This is also a terminal because both sides comes to the center. They got nowhere to go. They got
Okay.
nowhere to go. Remember?
Yeah.
There you go.
I don't think we talked about this before because
We
before
did.
we did.
We did.
Because
We did. I can show you examples that we did on this also.
maybe I forgot because I remember we saying it's 0 because it's at the centroid.
Yeah, it's at
Before.
the centroid also, but it's also a terminal, right? It has nowhere to go, right?
Okay, makes sense. Thank you.
Okay. Okay. The next problem I'm going to do again is a compound loading. It is really not difficult, but it has a lot of components. So this structure that I'm going to show you, basically it has a normal, it has the axial load, bending moment in two directions, shear forces, and also a torque. Okay, this one got no torque. Okay, the one I'm going to do now has a torque. Okay, this problem over here. Okay, that's it. This is one of the worst. Okay, the good news is about when it's a shaft, okay, or when it's a diameter, the second moment of area about Ixx and Izz is the same. That's the only good news. The rest, not good news at all. Yeah. Okay, example number 2. So you can see how our structure is loaded now, right? You can see that this is not a straightforward loading. Okay. So the diameter is that you don't see that the question asks. I forgot to write out the diameter. The diameter is one. I'm looking for the. Okay, the diameter of this shaft is equal to 1 inch. Yeah, this is a 1 inch diameter. So so the first thing, so we are going to determine the stress state. For element A and element B. Okay. So the formula. So first of all, we decide on our transformation. So for this case, the way it's drawn is different now. Okay, so this is our X, and this is our Y, and this is our Z. Okay. And point A and point B are elements, like what I mentioned before. We have first draw the centroid relative to the element of interest. So this is where the centroid is. Right? So this over here is our centroid. So from here, the formulas, okay, for now, we take it as we don't know what stresses they have, okay? So we know that we are going to find stresses in the y direction. Okay, normal stress, because the centroid is aligned with the y direction, right? So that's why normal stress is in the y direction. And this is equal to Py over A plus or minus mx over Ixx multiplied by Z plus or minus mz over Izz multiplied by Y. One thing is for sure, we know that Ixx will be equal to Izz, and this will be equal. So there's if this question does come out, I do provide you with the formula. Okay, so this is the formula. Okay, so it's equal to pi over 4 r4. Okay, so pi over 4 multiplied by the radius to power 4. Okay, so for our case, you know that this is equal to pi over 4, 1 power 4, right? So pi divided by 4, 0.785. Okay, so I'll do the 4. Is 0.785 inches to power 4. Okay, so get the information out, and we know that for this Z and Y, okay, is equal to 1 divided by 2 inch, right? Because it's the radius, right? Then the next formula that we're going to apply, where we have shear stress, is equal to the torque in the y direction, okay, over J multiplied by C, right? Then again, you have plus or minus, you have Vx over Qz. Oh no, what do you mean? Izz Qz over T, right? And then plus minus Vz over Ixx Qx over T. So we also know that C is equal to ½ inch. And we know that J is equal to twice the polar moment of area is twice the second moment of area. Okay, so this is 2 multiplied by 0.785. Okay, so 2. So it's 1.57 is equal to 1.57. Wait, shift pi divided by 4, 0.785. 0.785 times 2, 1.57. Okay, so get all this information out as quick as possible. Okay, so next we are going to look at our calculate our moments, our torque, so on and so forth. So I'm now going to look at the YZ plane. Okay, so we have our XZ plane. Okay, so I'm going to change the view. So this is Z, and then this is our X. Okay, so XZ. Okay, so you want to sketch this, it will look like this. Okay, it will look like this is just a sketch. Okay, then we are going to draw our centroid, right? Then relative to element B, element A. So this is our element B, and this is our element A. Then we put our forces. We have 600 pounds. We have 500 pounds. And then we have something that's coming towards us, which is 800 pounds. Okay. So from here, we can write out what we can see. And we know, let's look at the 500 first. Okay. So the 500 is acting exactly onto the centroid. Okay, there's no perpendicular distance. So we know that Vx is equal to 500 pounds. And based on the formula Vx equal to over Izz Qz over T, right? We know that the shear, which is equal to Vx over Ixx Izz, sorry. qz over t. So if you look at here, element A will be equal to 0 for the shear. Element B will be at its maximum, right? This is because the qz at A is equal to 0. And the qz at point B will be q max. So if I were to draw the shaft now, maybe if I were to draw the shaft, right? This is where the centroid is, right? And this is where our 500 pounds will act, right? And this is our element A, element B, right? And this is the axis of the centroid of interest. So for this case, this is your IZZ axis. Okay, so this is where we have our ZZ. So the shear flow, okay, will look like this. At point A with 0, and then at point B, okay, it'll grow bigger and bigger. This is how the shear flow is flowing. So that's why point B, you have maximum because it's at the centroid. Point A, there's no first move area, is equal to 0. Okay. Why not we take a 5 minutes break? We come back at 8:15 or 8:16. Okay.